All right, hello again, Dr. P here. And in this lecture, I'm going to talk about using protecting groups in synthesis. And the purpose of using a protecting group is to convert a reactive functional group into a less reactive functional group. After that, we'll do whatever chemistry it is we're trying to do on a different part of the molecule. And then we can convert the functional group back to the original one. Now, remember, this is going to be something that we use if we have multiple functional groups in a molecule. If we just have one functional group, we don't need to do it because there's only one functional group that can react. It's kind of like how in the electrophilic aromatic substitution synthesis problems, some people used blocking groups, used the sulfonate group as a blocking group when they didn't need to. So if you don't need to use a protecting group, then don't use one. But if you need to keep something from reacting, then go ahead and do that. Now, the main example that we've seen, the one that I mentioned in class, was protecting carbonyls by converting to acetals. Okay. And again, we would have something like, let's say, R, C, R prime, double bond O. And a great thing to actually use here is the following diol. So this diol means dialcohol, and this is actually just ethylene glycol, but 1,2-ethane diol would be the name. And with acid present, we will go ahead and get now our protected carbonyl. Okay, so just to sort of highlight here, here's our carbonyl carbon, it's right there. And then our oxygens from our alcohols, if you will, quote-unquote alcohols, are there and there. They just happen to be connected. So this is our 2 moles of alcohol is just in one molecule. Okay, so it's convenient because, you know, it's right there. Once one forms and you get the hemiacetal, then it's pretty easy for the acetal to form. Okay, so let's take a look at some examples. All right, so examples So let's propose a synthesis for the following. So let's see, what do we need to do? Well, I've got 1, 2, 3, 4 carbons, and here I've got 1, 2, 3, 4, 5 carbons. So I'm adding a methyl group. And then also, my carbonyl is being converted to an alcohol. So we'll say turn C double bond O into COH. We'll say HCOH. I guess there's no extra hydrogen, so we'll just say COH. So how are we going to do that? Well, let's think about this for a minute. What ways do we know to make new carbon-carbon bonds? Let's see. Well, we saw the Diels-Alder reaction. We have electrocyclic. Those aren't going to be too helpful. Oh, wait, we've got the Grignard. That should work pretty well because it creates a new carbon-carbon bond and gives us an alcohol. So if we were to do a Grignard, and get this, the only problem is that we can't just do a Grignard on our starting material because the Grignard could add to either carbonyl. So we have to protect one first. So let's do that. And if we just use one equivalent, 1 mole per every mole of reactant, if we just use one equivalent of our ethylene glycol, we will get our aldehyde protected. Now we can do our Grignard. And we will end up with that. And actually this second step here, the second step of the Grignard to quench, because remember our Grignard adds in and then we have an O minus, we quench with acid. Well, that's actually going to hydrolyze now our acetal back to the aldehyde. So this is one example. Let's take a look at maybe another one. All right, so let's say we wanted to do the following. Okay. So what we can see here is that we've added this whole bit over here. Now we could try doing a Friedel-Crafts acylation. With something like this. And then we'd have to reduce. We'd have to reduce that guy there. But we couldn't reduce the ketone without also reducing the aldehyde. So what we would want to do is do the Friedel-Crafts and then protect and then reduce. So it would look something like this. Now we'll go ahead and reduce. And in this case, we don't want to use zinc and aqueous hydrochloric acid, or the zinc mercury amalgam, I should say, and aqueous hydrochloric acid. We don't want to use the Clemensin because that would hydrolyze our acetal back to the aldehyde. So instead, we'll use H2NNH2 and KOH. So that is our Wolff-Kishner. And I think in a future video I'll show you a bit of the Wolff-Kishner mechanism. And that's going to, because it's in base and our acetal is resistant to base hydrolysis, we only reduce at the ketone carbon there and not at the one that is now the acetal. Now we can go ahead and hydrolyze back. And there we go. Now I should point out that other groups can be protected as well. So alcohols can be protected by turning them into ethers. And often we'll use like we could use like a tosyl ether or something like that, which is easy enough to do. Now, we've done this before to make the tosylate as a good leaving group. But in this case, now we've protected, and so we could have, let's say, a strong, let's say a base come in that otherwise would deprotonate and might deprotonate somewhere else on the molecule. An example could be, let's see, trying to think of a good example here. Yeah, it kind of depends. There's other things that we could protect. We could protect an amine by turning it into an amide, which is a carboxylic acid derivative that we'll see in a couple of chapters. So if I react this with acetyl chloride, I now have an amide, which is not, which is not nucleophilic. This guy is not nucleophilic. This is a good nucleophile, not a good nucleophile. This is also basic, and this is not basic. So now I could do some other reaction. We could, let me think of, there are ways of protecting an aldehyde instead of a ketone, and that would involve, I should say protecting a ketone instead of an aldehyde, and that would involve turning the aldehyde into something else that is less reactive. So for example, we'll say ketone versus aldehyde. Turn aldehyde into carboxylic, I'd hope if I could spell right here, into carboxylic acid. So in the previous page, I'll just flip back here. The previous page we saw, or pages, we saw how we protected the aldehyde and reacted at the ketone. Well, what if we wanted to protect the ketone and react at the aldehyde? So what we can do now is we'll go ahead and use something like chromic acid, so H2Cr2O7 and H2SO4, and that will give us now a carboxylic acid. And now I could make my acetal. Now my carboxylic acid will not form the acetal like the ketone will. If I really wanted to I could even try to make this into an amide or something. Now I can do some kind of chemistry to my carboxylic acid. So let's say I wanted to, reduce this to an alcohol. So now I can use lithium aluminum hydride, and so we'll say LAH and then water, and that will give me, I apologize for squeezing this in here. Oops. Here, let's do this. Let's go ahead and that's not what I wanted to do. I wanted to select this. So let's go ahead and select this whole thing here. And copy. And now paste. There we go. Excellent. And now we'll go ahead and get the following product. So if we use enough lithium aluminum hydride, we'll go ahead and reduce our carboxylic acid all the way to the alcohol there. And now we could go ahead and treat that then with H3O plus. And now we've turned our aldehyde into a primary alcohol, and we've left the ketone all alone. So some of these examples are maybe a little, I don't know if I'd say trickier or more advanced. They're reactions we haven't seen yet. But as we talk about them as the semester progresses, I'll be sure to mention them, and you'll probably see them in synthesis questions on quizzes and exams. I would say that for the next quiz, you'll definitely want to be able to do this type of protecting carbonyls by converting to acetals. So something like the Grignard that we saw here, or something like a reduction where only one group gets reduced. I'm not going to have protecting alcohols, I think, definitely not amides. And this is a little more advanced, so not on the quiz, but it could appear on the exam. But, we can practice some more as the time goes along. All right, so if you guys have any more questions about using protection in synthesis, because after all, good chemists always use protection in lab, stop by office hours and we can talk about synthesis. Or if we've got some time in lab, you can ask me then. Until then, stay safe out there. Bye now.